afternoon, everyone. So it's my pleasure to welcome you for an afternoon of insightful presentations. We'll have a series of 3 seminars featuring researchers with whom I've been collaborating. For the first talk, I'm pleased to welcome Antonia Bertolino, presenting a seminar titled Applications of Cross-Coverage to Test Functionality Equivalent Programs. So Antonia is a research director at the ISTI-CNR in Pisa, Italy. She's a distinguished researcher known for her significant contributions to software testing and software engineering in general. So Antonia, the stage is yours. Thank you.
I have mine. Thank you. Thank you very much, Breno, and thank you to all for being here. Boa tarde, that is one little thing of Portuguese. And I am very pleased to be here, actually to return back to this university. After a few years, I was already visiting UFP some years ago. And as Breno introduced, I am mostly working in software testing, with whom we have had a lot of joint work. And today, the talk that I will present is some novel idea on top of something that is quite traditional, quite old, that is coverage testing. This work is some research that is still ongoing in collaboration with a colleague of mine in ISTI-CNR, Felicita Di Giandomenico and Francesca Lonetti, and another colleague from another institute of CNR, that is Guglielmo De Angelis from IASI-CNR. And I have also to pay this, and before going actually into the cross-coverage testing talk, I want also to leave this slide for your attention if you are interested in flakiness. That is also some work that we did in the past with Breno, Miranda, and the other speakers today. So this is another recent result that we have presented in Information and Software Technology, is open access. So if you are interested also in flakiness, I was not decided if to present the cross coverage or flakiness in vivo, and so now you can have both with the same price. But okay, let's go back to the topic of this talk, that is cross coverage. Let me introduce the intuition behind the work. So I assume that most of you know this idea of coverage testing. That is one of the oldest idea in software testing. So you have some test suite, I call it T0, and in coverage testing you measure what is the coverage that you achieve on the source code of the program being tested. You can measure, for instance, which statements are covered or which branches are covered, or there exists other fancier way to measure coverage. So, and the idea is that coverage, why is it attractive? Because it provides a very intuitive, very easy stopping rule. That is, if the coverage that you measure is sufficient, then you decide that testing is sufficient and you can go ahead. If you still consider that the measure of coverage is low, then you can iterate and add more test cases to T0, trying to raise the coverage. This idea is quite used even in industrial testing. It's also interesting because you can automate a lot. There are many available coverage monitor that you can use. And also, there are also more sophisticated tools that can help also in the stage of deriving the additional test cases. For instance, EvoSuite, that I will use later in the evaluation, is one tool that, given the current coverage measure, can suggest you additional test case to cover the statement or the branches that you have not yet covered. So this is the idea of traditional coverage, and as I was saying, it is a quite popular testing approach since the beginning of the software testing discipline. So there are some assumptions behind the application of coverage testing. The basic one that I always explain, the very first lesson that I lecture that I do in software testing is that the idea of coverage testing is that you want to be sure to activate all the bugs that are distributed in the code. You can never be sure that if you execute a part of code, you are able to raise the failure of that bug. But the opposite, you can be sure. If you do not execute that bug, you will not show the failure. So it's a minimum requirements that you need to be able to observe the failure. In coverage testing, there is somehow the assumption that the usefulness of test cases depends on augmenting coverage. So if you use coverage testing, you consider that test cases that do not increase coverage are less useful than other redundant test cases that continue to cover the same entities. Then there are also limitations in applying coverage testing, because all of these needs that you can access the code. You need to have the white box or glass box for the code. So you need to be able to observe the code and modify the code that you want to test. This is one limitation, because this is not always the case. And the second, one other limitation is that only relying on coverage testing, so considering that additional test cases that do not increase coverage are less useful, is a sort of tautology. Because, for instance, you can have, if you continue to test, so to cover all the lines in the code, but this code is missing some functionality, is missing to do something that it should do, you can never discover this doing coverage testing. That is why we normally try to combine coverage with functional testing. So, continuing on this reasoning, what coverage testing tell us about the code that we test? So at a certain point, we started discussing that if we have two programs that are functionally equivalent, two programs that are conceived to implement the same specification, if we have a test suite that covers one program, the code of one program, does this coverage of program P tell us anything about a different program Q that is equivalent to the first one? Or I state the same doubt in a different way. If we have two programs, P and Q, that are considered to be functionally equivalent, why, if I take one same test suite and exercise this same test suite on both programs, why do I achieve different, very different coverage measure? I can begin to suspect that maybe the program are not really functionally equivalent, because the same test suite exercise them with quite a different measure. So, from this suspect, we introduce the notion that we explore today, that is cross-coverage. This notion is invented by us. It did not exist before, to understand. So cross-coverage, we define in this way. If we have several programs, P1, P2, Pn, that are supposed to be functionally equivalent, then if we have a test case Ti that we derived, for instance, using EvoSuite to cover program Pi, cross-coverage testing is consists of using this same test case TI on the other program PJ, with the J different from I. So cross coverage means that I measure the coverage on a program, and then the same test case that I know that increases the coverage of that program, I use to exercise the other program. So back to the intuition, with this notion of cross coverage, we propose that we can use the very useful notion of coverage measure that we saw as several advantages to test programs that are different from the one that on which we measured the coverage. And I am going now to show some example of how this idea could be applied in practice. Is all clear so far? Okay. Okay, motivating example. This one is in fact the very first example that actually triggered the whole work. So as I said at the beginning, this is joint work with De Angelis, Di Giandomenico, and Lonetti. Di Giandomenico is not a software testing scientist. She is a fault-tolerant scientist. So together with her, we were exploring how we could test redundant programs. So in N-version programming, the concept is that we use multiple programs that are supposed to develop the same functionality as redundant copies to ensure that the system is tolerant to failure. So this is applied in airplanes, for instance, energy system, so system where you cannot afford to have failure. So we use N-version programming, and so we have one specification that says what the program should do, but then the program is actually, the system is implemented by redundant program. So the very trigger of this idea of cross coverages was, okay, how can we test this redundant program P1, P2, P3, and so on? So this is the first idea that we developed, okay? So in the figure, you have three programs, P1, P2, and P3. We have the specification, the dark green, and from this specification, with some model-based approach, for instance, we derive a test suite. This test suite is to test the system, right? It's not to test the code of the program. Then we exercise this same test suite on all the three programs, P1, P2, and P3. And we apply coverage measure, and we measure C1, C2, and C3 that are the coverage achieved on the three programs. Now, if C1, C2, and C3 are quite different, so some small difference could be acceptable. But if there are big differences, I start to suspect that the three programs that should be redundant, should do the same thing. Actually, they are not. So what we propose, for instance, as an application of cross coverage, is that we start to augment the program that has the least coverage. Suppose C1. Suppose that C1 is the lowest value between C1, C2, and C3. So on P1, we can exercise some coverage analyzer. We derive more test cases, and we use the additional test cases to test not only P1, but also P2 and P3. So in this case, we have an augmented test suite that is T0 plus Ty, that are the test cases that have been derived from the coverage, to augment the coverage of P1. Then we can also consider that this same approach can be iterated. So following, we could then apply the same approach to another program and so on, until for all three of them, we can raise adequately the coverage. So this was one first application. As some terminology, the test that is derived for covering a program PI and then is used to test a different program PJ, in this case with relatively to PJ, it will be called a cross test. Okay, second example. This example was inspired by this work from Lemos et al. That were suggesting to use test-driven development also to search. Suppose we need some procedure, for instance, that make sorting of integer number, and we want to look in GitHub or wherever in some repo if we find some already existing program that does what we need. The idea of this approach, test-driven code search, is that we use a test-driven approach. That is, we want a program that does sorting. We first derive the test cases for this program. Then this same test suite that is called here T0 is applied not only to test the program, but also to search in the internet, in GitHub or wherever, the program that pass this test suite. And if the program pass the test suite, then the program are likely suitable for our need. Then suppose that we find several programs looking in the internet. How do we choose among all three of them? Again, cross coverage could come in to help us to make the selection. So we apply, similar to what we did before, we apply coverage measure to each of the programs that we find, but in this case, we cumulate in one common test suite all the test cases that augment the coverage in one of these programs that we find. And then after this, we could use this augmented test suite to select the program. And in this case, I would select the program that has the highest coverage, because this means that the program has less hidden code, has less code that is not clearly useful to me. Okay? And finally, this is something we are experimenting right now. Could be applied if we could extrapolate cross coverage also to test proprietary software for which we do not have access to the source code, but still get advantage of coverage because we measure the coverage on another program. So we have a trick of doing having the advantage of coverage testing, but for a program that we can only access black box. So the idea here is that we have a specification and we have a test suite that I call here compliance test suite, to say that this test suite is developed to guarantee that the program is compliant with what is required in the specification. And then we have two different implementations, but actually we want to test PJ, that is black box. How can we apply cross coverage for this case? This is even simpler. So we have the specification and the compliance test suite that is applied. then we use an equivalent program for which we have the code to augment the test suite, and we use this augmented test suite for the black box testing. And this is something we are experimenting just now for instance, the XACML for the PDP that authorize the XACML policies. Okay. How am I doing for time? Okay. So evaluation. We did some evaluation because so far I show you some idea. Does it work? Do we have any usefulness in practice? We did some evaluation. So this one, as I was saying, is ongoing. Stay tuned. I am not presenting the evaluation for this compliance test suite because we are doing the experiment right now. The other two experiments have actually, the other two cases have already been evaluated, and the result that I show you, I have the reference in the last slide, were presented in AST last year. So we were lucky enough to find some group of equivalent Java program. Here is the reference, where in that work that is completely independent from the cross-coverage notion, the author were showing that testing could be used to show functional equivalence. So what they provide in this work was a large set of program that is actually more than 700 program, grouped into 276 groups of equivalent programs. And in addition, they provided the test cases for this group. And in this study, they were showing that the test derived using EvoSuite for all the programs that are in a group were all successful when executed for all the program within one group. So functional equivalent in a formal method and so on can have a very different definition. For the purpose of this study and for the purpose of cross coverage, functional equivalent means exactly this, that the program have the same result when executed with the same test cases. Now, of this big number, we had to make some selection to conduct our experiment because we needed all the examples that I showed you before start from some common test suite. Instead, the program come each one with their own test suite derived with EvoSuite. We didn't have in the repo the functional test suite that was derived, so to say, from this specification, for instance. So we applied the Randup, that is a very well-known tool that can derive for Java programs random test cases. And we derived a common set of test cases for each group applying this Randup. So to be sure that we did not bias the study. But we could only do this not for the whole set, but for these 336 methods, still a good number, that were making 140 group of equivalent program. And then also we measured the coverage, the coverage, so we needed to apply the EvoSuite test cases to each of the other program, but some of these programs were too simple to have that their coverage was augmented. So we only kept those group of equivalent program for which it was possible to apply Randup and for which it was possible to increase the coverage. Then we asked these two research questions. The first one is a bit artificial because we asked, can cross coverage, the notion of cross coverage, help to increment the thoroughness, so the coverage of a test suite. So the cross tests are useful, and in this case, to this usefulness we measured by evaluating the additional coverage of the cross test. That is a bit follow me, it's a bit artificial, because actually, if for instance we want to use cross coverage for program for which we cannot measure coverage, then it is artificial. But for us, this is a proxy measure to understand if really a test case that is derived on program PI that increments the coverage of PI, when executed on PJ, is also useful to increment what we observe in PJ. Okay, so this was the first research question. So to answer, we had this procedure. As I was saying before, we have this common test suite T0 that is derived with Randup, that is applied to all the test, all the programs that are equivalent within one group. And then for each of the program, we measured what I called the cumulative cross, the coverage of the cumulative cross test suite. That is, if a test case has been derived to increment the coverage of program PI, I use this test case, I see if it is increase the coverage in all the other test cases except PI. And then we measure the coverage increase achieved by this cumulative cross test suite with respect to the initial test suite T0. And this is the definition of cumulative cross test suite, what I just told you, no? All the tests derived to increase the coverage of one program altogether for all the other program. And the results were quite promising, because we measured both the statement and the branch coverage. In this histogram, in the horizontal axis, the number corresponds to the ID of those 300 something programs that we kept. And on the vertical axis, we measure the increase of coverage. And on average, we have that the coverage increased of 26% for the statement and 33% for the branches. But this also was not uniform, because there were some groups in which we could not increase the coverage, but there were also some groups in which the coverage increase was in this highest quartile. So I think it is a first good result that suggests that using cross coverage could be a good idea. But then I would expect that you challenge me, right? Because if I test a program with 100 test cases, and then I test the same program with 120 test cases, whatever is the way that I increment the test suite, I could be anyhow increasing coverage just because I am doing more test cases. So we did our homework well. And we used also random augmentation, okay? And in all cases except one program, now I do not remember exactly the detail of this program that did not do better than, but it was a very strange program functionality. So on average, we increased the coverage better with the coverage-driven test suite rather than random. Okay, so this confirms that the idea could be useful. And so far, we have only been evaluating if the test cases could be meaningful. The second research question, I think, is more interesting, because now we move to see if cross coverage could be useful to find bugs. And in particular, one thing that I was looking for was if you remember my example, why I have so different coverage measure between two programs that should be equivalent. Maybe that one does not actually implement all the functions. So could I use this to find if I forgot something? That is the limit, the very limit of coverage testing. Coverage testing by construction can never find missing functionality, but cross-coverage testing maybe can. So we did another experiment, a bit complicated. And we used a sort of mutation. The mutation were that in a systematic, who know what is mutation testing? Okay, for the other, mutation testing is a technique quite used now in software testing, in which I deliberately introduce some small error in the code of the program under test, and I use this to evaluate the test suite. The intuition is that if my test suite finds the error that I know that I introduced, then the same test suite, probably there are also empirical proof of this, can find other errors that are there and that I do not know. Okay, this is the general idea of mutation testing. Here we applied a variation, because in mutation testing, traditionally, we make systematically change of all the operators. Arithmetic operators are mutated, variables are given different names, what else? Number of functions are changed, lines are removed. So there is a list of things to do in systematic way. Here we only apply the mutation to remove some functionality, and to be sure not to introduce bias while we did this, we removed, like in a systematic way, the first lines or one of the first part of an if statement for all the 300 something function. Then we need that this mutant that we did, that we do, can run. So finally, we found we could obtain only 169 valid mutants. So mutants that have missing functionality and can be executed. In all of these, we evaluated the if the test cases that in the first research question were executed from the cumulative cross coverage could detect the missing functionality. So in total, considering the equivalent method, we had 183 test classes. And finally, we see which of these 169 mutations that we inserted was revealed. And the results were very good. 124 that were more than 73% were killed. So let me make a summary of what this means in our intuition. Go back, for instance, to the 3 equivalent program that we use in fault tolerance testing. This result tells us that if one of the team, because in fault tolerance testing you want that the 3 programs are developed by different people, otherwise we lose the independence. If one of the team that develop one of the equivalent programs forget something, with the cross-coverage approach, we can score this, we can see this. So I think it's very promising idea. So going towards conclusion, we started with the assumption and the limitation of cross-coverage testing. And we said that one assumption and the limitation of coverage testing is that we need to be able to instrument and access the code. But this is not true anymore if we apply cross-coverage testing. Same is this, that as I was saying, by construction, coverage testing cannot identify missing functionality. But if we use cross-coverage testing, so if we check the coverage not on this program, but on another one that is assumed to be doing the same thing, we could even spot missing functionality. It is very promising. Okay, so we are done. In this talk, I introduced the idea of cross-coverage, the notion. And we show you some initial result of a benchmark we did. What we tried to do in this benchmark was not to introduce bias. So we tried to use programs that we found in a public repository. We tried to be very careful in making all the application. And we could see that cross-coverage can help increase coverage. So cross-coverage using another program to test your program can increase coverage and can help to detect missing functionality. And we are continuing to experiment on this. As I said before, an initial part of this was presented in this paper. This is the reference. At this address, there is the replication package with all the data. It's a lot of data with all these hundreds program that you can use. And we would be very grateful for any comment, any suggestion, any question you have now. That's it.
So thank you very much, Anto, for the very insightful presentation. Questions?
Hi, Antonia. Thanks. Presentation. So maybe correct me if I'm wrong or misunderstood, right? So the loop thing generates tests, but there is already a test suite. So you only keep the tests where coverage is increased. The setup of the empirical study. I wanted to confirm, and then I was curious on why then for the coverage does not increase at all for some.
So okay, there is some background to be known about the genesis of the repository that we used for the experiment. So the repository itself was not built by developing the program to be equivalent. Even the repository that we used, for which I gave the reference at its inception, was built by looking for equivalent program. And there was also a lot of manual verification that they did, to which we are very, very grateful.
Okay.
So, but the repository that we found came with, say, 5 programs that are, say, the equivalent. We had hundreds group. So suppose a group with the 5 programs. For these 5 programs, we had for each of the 5 programs a test suite derived with Evo suite.
Okay.
But for our experiment, we needed to start from one common test suite that is from the specification, is not generated considering any coverage, and then we use cross coverage to increase the test suite. So this is where we use the run loop. So initially we completely forget about the test cases that are given with the repository that were coverage driven. We forgot about this. We derived a test suite with the run loop. That the test suite was run on all the program, and then we ran the test cases that were in the repository that have been developed using Evo Suite, and we see if these can augment the coverage. If they increase the coverage, we keep. If they do not increase, why? Because maybe that the test that I am trying now is testing something that is already run loop test suite. Can happen, no?
Okay, I see.
Is it clear?
Yeah,
No, because I understand that it is quite complicated, all the experiment to
and
be.
you're relying on the previous data set as well. So
Yes. So now I presented this work also in ISTI. It was me that presented. And I understood that at the time it was not very clear. So now I try to be even more exhaustive in trying to explain, because it really conceptually it's a bit complicated. But the paper that I this year has all the details. Thank you for your question.
Thank you.
Thank you for the nice talk, and it was interesting to see this idea. I was wondering whether you thought about trying to solve this theoretically, or whether this would be a thing. So, for example, the assumption is that the programs are semantically equivalent. So maybe they have to be some kind, also have to share some similar aspects in the implementation. So maybe there's like some transformation rules that you can, like semantics preserving changes to a program. And then you could say, okay, for this transformation, coverage will change by this amount, it will be lost or won't change, maybe.
We have a lot of discussion like this when we talk about the paper continuously.
Okay.
And I am the one that I am going in this direction and say, because some other co-author says, yeah, but this is for augmented coverage, so maybe this is doing something that is not of interest for PJ, because it is. And I keep saying, okay, but the test case is you give an input and it gives you some output, whatever is the way that you generated it. So there must be some meaning, and I think it is close to what you're saying. Yes, maybe now it's completely empirical, the research, but maybe doing also some more theoretical coverage of the concept when we understand it even better would be very interesting.
Okay, thank you.
Maybe we can get in touch later.
Yeah, I would like to.
Okay, thank you. Any other questions?
Hi, so thank you for visiting us and for the talk. I was wondering about the first motivation on testing fault-tolerant systems.
You want I go back?
No, just that's fine. So in this situation, I think that in addition to being developed by different teams, sometimes the redundant software needs to adopt different technologies. In such a situation, I think that you would need to port the test cases from different technologies. And by doing that, you may introduce a new variable into your setting, because the ported test may not be equivalent to the original one. So I would like to hear your comments on this.
Yes, absolutely. This is a very good question, because to decrease the possibility of dependent fault, that different versions are subject to the same fault. The idea should be even to have a program written in different language. So here we went for the simplest case that all the programs are in Java, but you could have, yes, that programs are developed using different language or even using different paradigms. Here I must confess that we are in preliminary stage for the moment. We were just discussing, I say this and I do not have any evidence of this, that we could perhaps try to go to this now very popular LLM and ask them to translate the test case from one language to the other, from one paradigm to the other, but we never actually went to this step for the moment. But yes, going deeply into the fault tolerance, if we have a program that not only are developed by different teams, but using, as you say, different technology or paradigm, yes, it requires much work to apply this idea. Yeah, I agree. You spot. So it's good. It means I was clear. Thank you. Thank you. Wow.
It's really a rough thought more than anything else.
Yes.
But could you somehow? So I was thinking about it. I couldn't. I stopped where my question comes now. so you could, so you're based on the fact that you have redundancy. You have 3 different programs which have the same functionality, right? Which led me to thinking, how do you measure the dissimilarity of the source code? And based on that, I was thinking, can you somehow use something like code similarity metrics to see what is happening to the code augmentation sort of doing? I don't know how much was clear, but basically to see where the different
Yeah,
software
but in principle, I would like that the code are dissimilar. So when you say measure similarity, maybe it should be low, right?
Which led me to think, like, how different are these? So do you have a metric or something to know how different these are?
No, as far as I know, but maybe Felicita on this can answer better. But I am not aware of how we can measure the similarity between the redundant program.
There are metrics which measure, it's like,
yes, of course you can apply,
ways,
but
like
I don't know
checkers, like
if in fault
source code
tolerance,
similarity metrics. Maybe
I don't
based
know
on
if
that
in fault tolerance
information,
they have done this.
because maybe you can have
point.
a whiter box approach. So you're doing already white box, I guess, but you can also amplify more what you have based on similarity metrics and say, look, this portion of code are similar. With these tests, we can just use one version. No need to rerun
but
them.
again, in fault tolerance, they want that are dissimilar. If they are similar, it's not good.
But I guess to some extent it would be.
I think they measure traces rather than code similarity. But okay, we can talk offline.
Yeah, exactly. Thanks.
Thank you.
Can I also ask a more question? It's just a curiosity. Can you go on the slide where this increase? It was for the first in the experiment for the first research question.
The histogram.
Yes. Yeah, this one. So I just wanted to understand, like, you have these peaks, right? So if I understand correctly, so these percentages, how much the coverage increases after you, let's say, augment the test suite?
The test was exhaustive in the sense that on top of the common random test suite, within each group, we evaluated the increase of coverage for each other cross test.
Okay.
If the increase of the coverage increased, we keep. If it did not increase, we don't keep. And each bar is the cumulative increase of coverage for those cross tests that we keep. So if you remember, we had like 300 here, 336. So I hope that counting the bar, they are 336. Okay, they should be. Yeah.
Okay, because my question was like, is so for example, wherever you have these peaks, is that due to something in the let's say ID itself, or some?
No, is that the program are quite different. So for some program, it's easier to increase coverage. For other,
I see. Yeah. So it's just like statistically, some of them will be.
Yes.
Okay. You don't. It's not that you have, I don't know, somehow some intuition of why for some of them.
Some of them were so simple, like almost linear, that it is difficult.
I see.
Other were very.
More.
Yeah, and so it was easier.
I see. Okay. Thanks.
So, guys, we have a last question here.
Yeah, so maybe jumping on to his question, but something that was wondering about is to be able to use that, not only like you need these functionally equivalent programs, but some kind of assumption between it, so you can call the same method, for instance, like an entry point or the test, even though you want also that they are dissimilar after past this method, then they can do different things inside. So that's why I think it kind of could make sense that if it's just the same method you're calling, but then it's drastically different, then okay, you have a test, it does nothing,
exactly.
Not much over here, and then like, okay, the test you generate, now it's drastically increases the coverage. Is that the case then?
Yeah.
That's kind of what's going on, right?
Yes,
Okay, I was a
exactly.
bit puzzled about those peaks as well. So yeah, thanks.
Yeah.
Okay, so let us thank our speaker again.
Thank you to all for your question and attention. Thank you. Thank you, Breno, for inviting us.
Thank you, Anto. Now I think we can stop now. All right, so for the next talk, I'm pleased to welcome Emilio Cruciani, a researcher at the University of Salzburg in Austria. Emilio presented a seminar titled Towards Expansion-Sensitive Multiple Roman Spreading. So Emilio, the stage is yours. Thank you.
Thank you, Breno. Okay, so I would like to say that this is a work. It's not published yet. It's under review somewhere. And it's a work together with Sebastian Forster and Tijn de Vos. And it's going to be about this rumor spreading, which is, let's say, a stochastic process on network. And it could be interesting from, let's say, several points of view, I hope. So it's not about software as before. It's not about testing. It's about this process on network. You can think of it as either as, I don't know, some social network stuff where you have a rumor that spreads in the network and you want to see how far it takes to reach everyone. But it's also interesting because you can use it as a, let's say, a smaller part of some distributed protocol to implement some distributed algorithm. Okay. So in particular, let's say there are 3 new concepts that we introduced with this talk, which are the multicolor rumor spreading. I'll tell you more about that. This class of graphs, which are called vertex expanders with some large phi. And then this more general theory, which relates the two and tells us about properties of rumor spreading on this class of graphs. Okay. So the classical model, it's also called the random phone call model. It was introduced in the 80s. And it works like this. So we have a graph. So during the talk, I'll just call n and m, the number of nodes and edges of the graph. I'm just saying it now because it will appear sometimes. So we have a graph and initially some arbitrary node as a piece of information, okay? And then there is this process that evolves in synchronous rounds. So at time 0, say, the node has one single node as information, and in every round, the information spreads according to some rule. Okay, and in particular, there are So what we're interested in for this talk are these kind of protocols here. So these rules here, which are called push, pull, and push and pull, which is the combination of the two. And in particular in push, what happens is that if a node has the piece of information, it will just call a random neighbor and push the information to it. So whenever the random neighbor which is called doesn't know about it, it will get to know it. In pull, instead, nodes that are not informed, so that do not have the, let's say, the piece of information, will also call a random neighbor. And if they call a neighbor that knows the information, they will also get to know it. And instead, in push and pull, these two operations happen simultaneously. Okay, so let's make it more, how do you say, with a figure. So suppose this is our graph initially, and the red node has the piece of information, all the others do not. So what happens is that red nodes just will pick a random neighbor and push the information to it, and white nodes will pick a random neighbor and will try to pull the information from it. Okay. So in particular here, at time, let's say this was time 0, at time 1, let's say that neighbor up there. So let's say that the original node with the information pushed it to a neighbor, and no other node, for example, this other guy here, maybe tried to pull from a neighbor that didn't know, and so it didn't get the information. Okay, and then at time 2, the information keeps spreading again with the same rules, until at some point the entire network will know the information. Okay. So what we're interested in this problem is trying to understand how much time, so how the number of rounds it takes for the information to spread in the entire graph. Okay, as a function of the size of the graph or of some other, let's say, characteristics of the graph. And in particular, the first results are about complete graphs. So every node is connected to all other nodes. Okay, and in particular, if you pick push and pull, let's say separately, or push and pull, which is the combination of the two together, what happens is that this process finishes in a number of rounds which is logarithmic with respect to the size of the network. Okay, so for example, suppose the network has 1,000 nodes. Of that will be, depends on the base, but let's say it's going to be base 2 is going to be roughly 10. Okay, and of course, since this is a randomized process, this happens with high probability. So with high probability, just take it, if you're not familiar with it, just means basically almost surely. Okay, otherwise, technically speaking, I don't know about the audience if you know about it, but it's going to be some probability that goes to 1 as n goes to infinity. Okay, so it's going to be a 1 minus a small o of 1. Okay, so these are the first results. So this is a theta, so we have both an upper and a lower bound. So that's going to be a precise, let's say, analysis of how long it takes. And logarithmic is typically quick. Okay, and what motivated our work was trying to see if it can maybe if this kind of process can make even quicker. Okay, but before going to that, I want to say a bit more about, I don't know, what's studied already in the literature, and in particular, the process has been studied not only on complete graphs but also on other classes of graphs, which is pretty, I would say. And the most famous, I would say, is what is called expander graphs. Okay, now, what is an expander? So very informally, an expander graph is a graph which is extremely well connected while being somehow sparse. Okay, so it's a sort of a sparser version of a complete graph. To be more precise, there are several definitions. To some extent, they're all equivalent in the sense that they're all they share some characteristics. Let's say this is the first definition, which is the one of conductance expanders. Essentially, it tells us that whatever subset of nodes S we pick, in this example is going to be the circle, so the 3 nodes there. Whatever we pick it, so as soon as we pick S, we basically induce a cut in the graph, which is this number of edges that cross from S to the rest of the graph. And a graph is an expander if this cut is never, so no matter how you pick S, the cut is never sparse, meaning that this ratio here, which is the number of red edges over the volume of the set, so the sum of the degrees of the nodes in the set, is always bigger than some parameter phi. Okay, and there are also other, let's say, definitions of this, like edge expansion, in which essentially we also look at the number of edges crossing the cut, but we normalize it not on the volume, but on the size of the set. And then there is this notion of vertex expansion, which is more important for this talk, where instead of looking at the edges crossing the cut, we look at the boundary of the cut. So this, let's say, partial, this ds is the boundary of S, which is the number of nodes, the set of nodes that share at least one neighbor with the set S. Okay, and so a way to see this class of graphs is it's typically important and studied because it has some nice properties, and it means that typically they are robust against, I don't know, edge deletions or stuff like this, meaning that if you delete something randomly, it's very hard for the graph to be disconnected, say. Or like it has also other, let's say, more combinatorial properties, or it's related to random walk. So they're extremely well connected. If you start from any node, you basically get lost very soon if you start a random walk there. So what about the results in this class of graphs? So we focus on push and pull because, as I said, so intuitively, this is going to be faster, right? Because you both push and pull simultaneously, and we want to make something faster than log n. So rumor spreading, the classic one I told you before, it has been studied on all this class of graphs. And in particular, we see, for example, for conductance expanders, that the time it takes is still logarithmic, but over this parameter phi. So if you start the process on a phi expander, the time it will take is going to be log n over phi. And since phi is smaller than 1, this is going to be greater than the time it takes on a click, which makes sense intuitively, right? Because you have less connections and this will take more. But it's a way of characterizing this fact, okay? So you have a graph, which is not a click, a complete graph. It's somehow a good expander, okay? And that's the time it takes. As soon as you look at the edge expanders instead, there is this strong lower bound of square root n. So square root n asymptotically is much larger than log n. So meaning that in this class of graphs, the process will be much slower. And instead, if we look at vertex expanders, well, the time it takes is, let's say, let's forget about this. Let's say it's going to be log square. So the log delta is maximum degree of the graph. So smaller than log square, still over phi. Okay. So this is what has been studied, and in a second you maybe understand why it's important for this presentation. Yeah, and as I was saying before, this is important because it's used as a tool for distributed algorithms. Okay, to design some distributed protocols, they can use this sort of process as a primitive. So what we want to study here is to try to understand first if there is some model that we can use, so some different protocol of rumor spreading, such that the rumor will spread faster than logarithmic time. And in particular, to make it simpler, here I say constant time. Okay, so we want to try to understand what kind of protocol for rumor spreading we need to just finish in a constant number of rounds independently of the size of the graph. And as a sort of, it's pretty natural, I would say. So what we study is this sort of trade-off. So suppose instead of rumor spreading, in rumor spreading, you like nodes communicate with a random neighbor. So now take this other protocol in which nodes just spread the information to all their neighbors. Of course, if a node with the information spreads the information to all its neighbor in a complete graph, this will finish in a single round independently of the size of the graph, right? So we study a sort of interpolation of the two processes. which we call K push and pull, in which in each round, each node doesn't sample one single neighbor, but samples K neighbors uniformly random, and pushes the rumors to them or requests the rumors to them from them. Okay. And in particular, still with the same picture, if we increase K from 1, which was the first example, to something higher, say 2, the process will be faster, right? Because, for example, here, the node maybe will push to both its neighbors. And then in a second round, many neighbors will get to know it. And very quickly, the process will spread. This is intuitive, right? Because K is bigger than 1, so the process will be faster. But what we want to analyze is how much faster and what's the trade-off between this K and the time. So how this number K has an impact in the spreading time of the rumor. And what we prove as a sort of first result is to analyze basically the process on complete graphs. So we prove that the number of rounds the process takes is log n over, when you see this log base K, you can think of it as log n over log K, okay? So basically the speed up that there is by incrementing K from 1 to something that's bigger, it's reducing the number of rounds, but by something which goes like logarithm of K. And in particular, if we want to answer our original question, so how much time, what model, so do we need for constant time rule spreading? This means that as soon as A is some polynomial in n, so n to some small epsilon, so square root n, but even smaller, n to the epsilon, we will see that these number of rounds will be basically 1 over epsilon. Okay, so for example, you take square root n, the process will finish in roughly 2 rounds, 1 round, 2 rounds. Okay, because it's going to be log n over log K, but K is n to the epsilon, so epsilon log n and log n simplifies. Okay, so the next step is basically study the same process with this K push and pull rumor spreading on other classes of graphs. And here I want to tell you why the class of graph we introduce, it's interesting. And so if we go back to the results I told you before about rumor spreading in expanders, so we see that in all of them, we have at least a lower bound on the time it takes. And we should observe this, there is this very simple observation that the diameter of the graph is always a lower bound on the number of rounds it takes for the rumors to spread. Because the initial information is placed arbitrarily in the graph. And of course, even if you each node communicates the information to all the neighbors, it will need at least diameter time to reach the 2 nodes which are farthest away from each other. Okay. And in particular, we know for this class of graphs how much is the diameter. Okay. So in particular, in conductance expanders, the diameter can be log n over phi, so it's bigger than log n, which means that independently of the size of K, so on the number of neighbors to which we spread or request the rumor from, the process cannot be faster than log n, okay? So it cannot take constant time. So we discard this class of graphs. So because the simple fact that the diameter on these graphs is bigger than log n, so log n over phi, and phi is smaller than 1, implies that the process cannot take sublogarithmic time, and in particular constant time, which is what we aim for. Okay, for edge expanders instead, there is this lower bound that is independent on the diameter actually. So it also works for graphs with small diameter. So we also exclude this class of graphs. And instead, if we look at vertex expanders, well, we know that the diameter is log n over phi, and the best known time for the rumor to spread, which is actually tight, it's only log n square over phi, okay? So it means that no matter how big K, the largest improvement we can achieve is a factor log n, which is not, again, enough to reach what we we hope for. So basically what we define here is a new class of graphs, which is interesting, at least for this problem. We believe it can be interesting also for others, which we call phi vertex expander for phi bigger than 1. Okay, so we have a way of defining that. I will go to it later. And what we prove is that this k push and pull protocol requires a time which is log base k. So basically log n over log k times log n over log phi. So as in the click, if k is a polynomial and phi is also a polynomial, which is allowed because it's bigger than 1 at this time, the time will go down to a constant with the same trick as before. Okay. And we also have a lower bound, which doesn't match. So there is time for improvement in this analysis. Okay. And the lower bound is just the sum of log n so base k and log n base phi. So let's go to this definition. Let's see if I can manage to give a sense to it. Okay. So basically, we have this parameter phi, which is we call the expansion of the graph. And it goes typically, let's say classically, in the classical definition of vertex expanders, it goes from 0 to 1. So we extend this range to be from 0 to n. This doesn't come for free because we need to restrict basically some property of this expansion. Okay. So in particular, we say that a graph G is a phi alpha vertex expander if this condition holds. So if we look here, we still have the ratio between the boundary, so the number of nodes in the boundary of a set, and the size of the set. But what changes, and I didn't tell you the details before, but is the fact that here, this property must hold for all sets which has a size which is at most alpha n. So in the classic definition of expansion, alpha is fixed to 1/2. So to give, which means that no matter how you basically pick a bipartition of the graph, you have this high expansion, meaning that fix a set S, it will grow a lot. Instead, here what we say is we look at sets which are smaller than that. So for example, if alpha you see is smaller, strictly smaller than half, not strictly, but smaller than half. So let's say 1 over 10. So you have a smaller set, which guarantees a higher expansion. Not guarantees, but can guarantee a higher expansion. Okay. So basically, this is a way of talking about this expansion of small sets, which already existed as a notion somehow, but never in this regime where phi can go larger than 1. So in particular, we proved some properties of these graphs. And in particular, if alpha is bigger than this ratio, 1 over 1 plus phi, so for example, if phi is bigger than 1, this will be greater than 1/2. This class of graphs, phi alpha expanders, doesn't exist. Okay, you cannot build one. On the other hand, if alpha is too small, basically the expansion property becomes very local to the point that the graphs can be disconnected. Okay, so it only holds for smaller components. And in particular, we also know that if we look at this class of graphs, there are properties of, we know some properties of them. For example, we know how much is the diameter. And we say that in particular, the diameter can be sublogarithmic for some range of phi, okay? In particular, if we fix phi in this range, which is, again, in between vertex expander exists if it's smaller than this and are connected. So we have a connected graph that can be built somehow because the object exists. You can prove how much is the diameter, and the analysis is somehow simple. So this is not a true one, but it's to give an intuition. So if we start, let's say, from a node V, what's the size of the neighborhood? So when I write this, is basically 1, which is the size of the node, plus the size of the boundary. So since the graph has expansion phi, you grow from 1 to phi. And if you repeat this argument, it will be basically you have something which is at least size phi, and it will be phi squared. So you can iterate this argument so that starting from a node, if you look at the k-hope neighborhood, this will be something roughly 1 plus phi to the power k. And as soon as k, it's basically log n base phi, so log n over log phi, you get that basically this growth reached more than half of the graph. So if you do it twice, there will be at least one common node, and the diameter, so the entire graph will be reached because there is the path between the two nodes. So you will have a diameter which is log n over log phi, okay, log n base phi. So in particular, as soon as phi is not a constant, so it's some small omega of 1, so let's say something bigger than a constant, the diameter will be smaller than logarithmic, which is what we want, right? Because the diameter is the lower bound. So as soon as the diameter shrinks, we can get something. So we have the hope that this K push and pull protocol is faster than log n, which is what we want. And in particular, if phi is a polynomial in n, so n to some epsilon, the diameter is constant, and we have the hope that if k is large enough, the rumor spreading time will also be constant. Okay, but so far we only exploited this property, and we still don't know about these graphs. So if they really exist, how can they be built, and stuff like this. So in particular, I want to give you some examples of this class of graphs. So complete graphs are expanders, are these phi alpha vertex expanders for every phi, and as soon as alpha is smaller than the regime for which they exist, okay? And in particular, also random graphs for some regime of P, which is the probability for a pair of nodes to be connected, are expanders in some range of alpha, okay? So we can prove this. And the fact, so basically these two examples give us the lower bound, okay? Because we have an example which is complete graphs, which I told you before about, in which we know that the rumor spreading time is log n over log k. Moreover, we know that Erdős-Renyi random graphs are vertex expanders, and it is known that basically the diameter of Erdős-Renyi random graphs is related to P, and if we pick P 3 phi over n, which is what we can prove the random graphs are basically expanders, we know that we'll have a diameter which is log n over phi, okay? So putting these two facts together, we get a lower bound for the process on vertex expanders, okay? Instead, let's say the main result, so combining everything, is that, so basically if we pick a vertex expander for this phi bigger than 1 and in the right regime of alpha, then with high probability, because again, the thing is randomized, the protocol will require this number of rounds. So this number of rounds simplifies to log n over log k times log n over log phi, as I told you before. And what is weird here is this basically strange factor, strange term. But what is interesting here is that if alpha goes to 1 over 2 plus 2 phi, basically this term goes to 0, so to 1 over 0, which means that the graph gets disconnected and the rumor spreading time will go to infinity. Okay. So how does the proof works? I'll just tell you the intuition. So it's somehow intuitively simple. We just exploit this notion of expansion, right? So we start from some, we call IT the set of informed nodes, so the nodes that have the piece of information at some time t, and we look at how many nodes are informed after, let's say, r rounds, where r is a function of k, so log n over log k. And in particular, we see that this is we can prove that this is, with high probability, a constant fraction of the boundary. And by expansion, we know that the boundary is at least 5 times the set. So this is not the proof, the idea behind the proof, okay? And basically, if we keep iterating this idea for log phi n times, we get the final results, okay? So let's say, yeah, there are some technical challenges here. In particular, the main one maybe is this fact that whenever you, let's say k is 1, so a node pushed the information to a single neighbor, you expect that if you increase k, the information will spread to k neighbors, okay? But this is not as easy because there could be, so the information could be pushed to the same node, to the same nodes. And so there, we need to find some way of, let's say, analyze this. And yeah, this is another problem, but it's somehow technical, and it's the fact that typically to get these high probability results, you do some concentration, use some concentration inequalities, which require the number of rounds to be logarithmic. But in this case, we don't have this. Okay, so we need a turnaround for that. And also the fact that as I said before, this expansion is just local, so it just works for sets which are pretty small. Need it to hold somehow also. So we need to prove this thing also for sets which are larger. Okay. Yeah. So in conclusion, we studied this process and we wanted to find both a model and a class of graphs for which we can finish this rumor spreading in a constant number of rounds. In less than log n in particular. And the answer is that for some, there exists this specific class of graphs, which has a very compact diameter, and for which we can prove upper and lower bounds in the spreading time. Okay. Yeah, and let's say a posteriori, so after we analyze all of this, we think that this could be used for other tools. For example, this expander decomposition, which is now very used in distributed algorithms. So it could be interesting to find it. So to find, for example, a decomposition of the graph, smaller clusters, let's say, where each of the clusters has this kind of property. And I think that's it. So thank you.
Thank you very much, Emilio, for the great talk. So, do you have questions? Let me see if I have something on the streaming. I have questions myself, but let me check first.
Oops.
So let me start with my question. So just want to make a connection with first talker, for Antonia. So for the things of graphs, but for the problem I have in mind, I think it should not be a completely connected graph. I'm thinking more about representing the modules of a software or the functions, whatever you want as a graph. So it might have leaves at some point, different entrance points. And I was wondering if some of the things that you showed us here could be adapted to apply for the problem of reachability. So for the reachability in a graph, so basically, that so if I entered for this point, this node, and I see my connections, I know that I can get to this other point, hopefully. And then in your case, you have a different problem. So the node knows the information, it might try to push information, other nodes might want to receive the information. So I was wondering more like I have traces, so it's not a one information. So the calls for the software, it enters from one point, probably from the same entrance point, and it activates some nodes. And then another execution, it will activate different set of nodes, and then this again and again and again and again. So after collecting all this information, all these traces, would it be possible to adapt some of this to have some notion of considering the way this software being used, that information, or let's say that this set of inputs can go up to this point, kind of define a bound for where which parts of the software you'd explore?
So, I mean, it's somehow similar in the sense that you have these paths going on, right? So there are two things here going on. One is the process, and the other one, so I'm talking about this talk, right? One is the process, and the other one is the class of graphs, which is somehow a bit specific, right? So if I understand correctly from what you said, what you described, is not really the same process. Of course, one could try to analyze that and see what can be done, but definitely this doesn't apply, you know, directly to this other scenario. So it could be interesting to see, like, so for example, if starting from this trace of programs that you're talking about, you have, so for example, do you know what kind of graph you can expect? Can it be any graph? Do you know if,
Anything?
yeah, sure. But do you know if there is some specific properties of it? That could be some interesting that can be studied. I don't know. And yeah, this, I don't know, it could be discussed. Definitely there is not a direct connection from this, but why not? Yeah.
Okay, thank you.
Thank you, Emilio. Of course, I am not expert in this, but somehow, stupidly, probably from your title, rumor spreading, I was thinking that the research would like to block the rumor spread, because rumor spreading I thought as a negative meaning.
Yeah.
Whereas here, what you get from your research and also the other previous work that you mentioned, you are looking for how to guarantee somehow that the rumor is spreading quickly. That,
Yes.
to me, in the modern times, seems not something positive.
I see.
So I would have liked to learn about research that say, how can we block rumor spreading, especially if rumor noise like fake news or
Yeah, or
negative
even a
thing
virus.
or virus. So is this propedeutic to the other direction?
I don't know. I know for sure that there are works in which you maybe have, there are more optimization works, right? For example, you have a graph, you have a fixed model for which the rumor spreads, and you have some, let's say, budget, okay? And you can, let's say the optimization problem would be something like you want to select K, so the budget nodes, such that they will not spread the rumor or the virus or whatever, in such a way that this will delay or block forever, you know, the spreading. This has been studied. So what I can tell you here is that this class of graphs, which is expanders, it's one of those class of graphs in which it's going to be hard to block the rumor. Okay, but also it's this specific one is also a very dense graph, which I don't think it's something you can expect in, I don't know, social networks or stuff like this, because it's very, very dense.
Yes, yes,
This specific
I see.
one. But generally speaking, you know, these expanders are hard to cut, to subdivide. So you could say that if a graph is a bad expander, then the problem somehow becomes easy because you identify the cut very heuristically. It's not easy, but let's say ideally you find where the graph, the cut is sparse, and you could place these blocks, you know, there so that the rumor doesn't spread.
Yeah, but your research instead assume that you are willing to spread as fast as possible the rumor, right?
Yes, because so the name is
assumption,
comes from the original thing.
Yeah.
So just called
So-
rumor spreading.
Yeah, but
and
it
we
could
want
be
to
information.
Exactly,
Okay.
exactly. And sometimes we want it to be fast because you can use this as a tool in some
Yeah, for
distributed
instance,
applications.
if it is an emergency,
Mhm.
like
Also,
that could
like
be
from
a
a
good,
more, you know, applied thing. Yeah, it could be some emergency and you want
Yeah.
to actually tell everyone. And that's
yes. Okay, thank
this
you.
kind of graph could help.
Thank you. So I think we have another question here.
Sure.
Could I say that rumor spread can be applied in contexts similar to epidemic models or no?
What? Sorry, I didn't understand.
Do you want to say or can I?
Oh, yes. Yeah. It's definitely related to epidemic models. So typically, it is definitely related, but typically in these compartmental models like SIR, SIS, I don't know if you're probably talking about this.
Yeah.
So the process itself is a bit different, right? Because you have some probability for nodes to say not be infected anymore. So suppose it's a it's instead of being a rumor. So suppose it's a virus. It could be that the virus spreads. Some people are are affected, but you could also be recover from the infection. Okay, so maybe you go to the hospital or take some medicine and you recover. So somehow there is a different kind of things that are studied, right? Either to say what are some parameters in the model, such that either the virus spreads everywhere or gets contained in some areas of the graph. But it's definitely related, right? It's still a process on a graph. It's
okay, thanks. And how may I decide which one is better? I know depend the context, but in general,
okay.
you have a preference or no?
So which one is better in which sense? I don't understand in which sense which one is better. So I think the way I see it is that they model different things. Okay, so in somehow, for example, these SIS, SIR, these compartmental models are good to model the spread of a virus or of something that can be. So, for example, about the information, it could be something that can be forgotten, right? Here, instead, we just assume that once you know the information, you will never forget it. So it's just a model of a different kind of, process on the graph. So they from a modeling point of view, they're just different somehow. They should be used for different scenarios. I don't know.
Okay, thanks.
That answers. Yeah.
All right, thank you. So let us thank our speaker again.
Yeah. Thank you.
For our last talk, I'm pleased to welcome Roberto Verdecchia, presenting the seminar titled Empirical Research for Greener Software, where two words meet. So Roberto is an assistant professor at the Software Technologies Lab of the University of Florence in Italy. So thank you, Roberto. The stage is yours.
Thank you, Breno. Thank you for the invite. Boa tarde. That's all the Portuguese I have. I'm sorry. So I'll start with some short question, just to warm up a bit of sensibilization on the topic. How much do you think software consumes? A lot or not a lot? Medium. Yeah, okay. Let's see. So, a big AI machine translator, it's like Google Translate, consumes 626,000 kilograms. To put it in perspective, how much do you think an American person consumes in a year? Everything included, flights, food, clothes, water. No right or wrong answer. I used to have 20. Like? Less than 6? Say 20 is 30? Oh. Huh? Jeez, you're so off. It's around 11. I mean, Antonella won, but it's, 11K. So to put it in perspective, you train Google Translate, and this was in 2019, back in the days where we didn't have LLMs yet. So it's about 57 people in a year just to train something like Google Translate. And I said, well, but it was back in 2019. We are improving things. Actually, this was OpenAI before it became what it is nowadays. Funny that I put in the slide back in the time, but what they stated is that resources double every 3.4 months. This is really bad, right? So this was an old-fashioned AI machine translator. Now we have ChatGPT. How much do you think ChatGPT consumes to be trained? So, make some calculation. That was 285K, resource double. More. 1,000. Actually, it's only 5. It's like it's less than double, I would say. So this prospect we have on the bottom is wrong, or is it? Then we look at how much we need in terms of carbon emission for a prompt. When you ask something to ChatGPT, that's also the part of inference, also consumes energy. What you see, it consumes like a third of what, maybe even more of a third of what you needed for training. And what is fascinating here is this is for a day. So it's not one shot that you need a lot of energy for training. It's each day, ChatGPT 3.54 now consumes that much. All the users, all the users. Yeah, it's really bad. It's like it was you that was saying about nuclear plants and whatnot. So naturally, the logic thread we're going to is to ask us, are we all doomed? And this was something that Bloomberg asked me yesterday, and I have not an answer to this, honestly. Maybe. But a question I have an answer for is, what can we do to improve the situation? And following a bit, what I was taught during many years of studies, one thing we can do comes from measuring things. So this quote, we don't know who said it. They say it's from a management consultant, but it's not true. But you can't improve what you don't measure. It's, okay, in the engineering field, right? It's like other things I'm not agreeing with. Like it's like, I can't measure happiness, so I can't improve it. No, I know if it's sunny outside, I will be happy if I don't measure it. But in the field of software engineering, I guess this is mostly true. And how do you measure this? Well, this is one of my go-to books. I guess we all know it in one version of another. Experimentation in software engineering. And I don't think we really need to be that discursive about it and give all the data, but you know who this guy is? You know? Yeah, he was born in Pisa because he's Galileo. I mean, so from the same region in Italy. I might be biased that I like the guy. And he's like, one of the founder of the experimental method, which usually starts with formulating a question. Then you do some background research, usually. You formulate some hypothesis. You do your weird experiments. You look at what comes out of the weird experiments. And then basically you analyze the results and draw a conclusion. This is like a very short version of what experimental software engineering is. And again, this is not, I guess we all know this, but what we consider in this presentation is in vivo experiments. I won't go in vitro, sorry. So in a controlled environment, I won't go into in vivo or in silico, in virtu. That's all for another talk, I guess. But usually, we have a set of independent variables we can fiddle on, and some we can't fiddle on, which is the observed variables, the dependent variables, such as, for example, test coverage, number of bugs, or execution time, or in the field of green software, energy consumption, mostly. And this is an example of an experiment on green software we did with the awesome people I had the pleasure to work with at the Vrije University of Amsterdam. Ivana Maravolta was teaching the course of green software, the Green Lab, I think it's called. And what we looked at is how much meeting apps consumes. So I guess it was Google and Zoom. So what we did is, as Galileo would suggest us, we formulated some questions such as to what extent different apps consume energy, or what is the impact of the number of participants on the energy consumption, or what's the impact of the camera usage, the virtual backgrounds, and using the microphone. So these are our questions we want to answer. We set up our experiment, which consists of installing, having a phone. There was a Pixel 3, and then an experimental setup where the data was sent to the computer, and then we started to make meetings, right? Simulate meetings. In this case, it was still in an in vitro environment, and we got the results. For example, in this case, we see that, who would have ever guessed it, using the camera consumes more energy than not using it. Maybe more interesting, we can see that the virtual background has an effect on energy consumption, but not that bad. So it's like, if you want to save battery, you could borderline keep your virtual background on because it doesn't consume that much more anyhow. And this was one example, and you could say, I mean, this was hard, but I don't want to undermine our findings or anything. But you can say, okay, you measured features in a black box way, you just plugged it in, run some things, but this was, kind of an easy thing to do. It's like we consider that software black box, and maybe you're really a geek and you like source code and so on, and so say, like, can we go deeper? And the answer is yes, of course we can. That's what we do. And for example, this was an approach to sort of locate the hotspots in a source code, so where more energy is consumed in a source code. And the intuition behind this, it's not rocket science, but basically we have software and we have different paths through it. Could be this bubbles, could be functions, could be lines of code, could be classes, whatever you want to like. And then we have some tests, and we measure the energy which each test consumes. So in case of test 1, we go from A to B to D to F, and this consumes a lot of energy. While in the case of test 2, we go from A, C, E, F, and this is all good. It doesn't consume that much energy. And based on this information, we can sort of understand the paths which consume more energy or less energy, and the hotspots, so where the paths that consume more energy all pass through, which in this case is... Emilio, you're a fast thinker, come on. Huh? It's D. I love for your caipirinha later. Maybe not. Depends. Yeah, in this case, it's D, right? It's like trivial, but little people focused on this so far. Weirdly, because I think it's really easy and efficient. And the beauty about this is that you can use a test suite which is already available. Just plug in something which measures energy, and then basically for free, you have to run the tests anyhow. So you just measure the energy on the side, and then for free, basically from a software deployment point of view, you get the energy hotspots you can improve. To topic with high potential, nobody basically focused on it so far. Two groups. This was some colleagues from Germany, and then some other people from Portugal. And also here, from an empirical standpoint of view, we have our little in vitro setup. We run the experiment, we measure the energy. In this case, we looked it was like, a proof of concept, and we took grep and the software infrastructure repository we all very well know of. And then we looked at which function consumed more energy, looked at the source code, and, theorized on why this were the hotspots. It looked like it worked. But, we said, AI consumes a lot. Can we do something also in that domain? And then the answer is like, well, obviously, this is what, as one of my fields, the fields I am currently focusing on, which is the field of green AI. So how can we make AI system more energy efficient? And this was, for example, a study we did with lots of colleagues from everywhere in Europe. And not because we have some, I think James Wickend is from the UK. It's not part of Europe anyway. Anyhow, and in this case, we looked at borderline Europe, Europe-ish. Huh? Is it? Oh, right. Okay. So everybody was from Europe. Errada. And what we did here is basically looked at, instead of fiddling with algorithms like hyperparameter tuning, designing new algorithms, we just said, what if trivially we just fiddle with the data? And so we looked, okay, first introductory question, do different algorithms differ in terms of energy consumption? But where the real meat is does the size of a data set impact the energy consumption? And again, what is interesting to know is to what extent, does the number of feature impact the energy consumption of AI algorithms? As in empirical research, we set up our empirical experiment. Okay, different algorithms consume different energy. Big surprise. Sure. This is about training. Yes. In this case, it's about training, which a lot of studies currently focus on. But then we see that a lot of energy is actually consumed in inference phase. Depends on Well, I know. we can't but improve in our research as we go, I guess. I guess until like 2 years ago, everybody was focusing on training. Now they're also shifting towards inference. Yeah, it depends on how much a model is used and how many trials you have before you are satisfied with the precision of your model. And what we looked at is that, of course, more data points you use and more features you use, the more energy you consume. But then you also look at, this is trivial, but then you also look at the accuracy of the model. This is in terms of F1 score. And in many cases, we see that actually a lot of data we don't need because the accuracy stays stable. So as follow-up question is, when can we stop, for example, in case of early stopping, and how many features are really needed? This is something we then improved on with some colleagues from Luxembourg, in which we said, okay, so in the trivial case, we just look at the number of data points, but how can we actually select high quality data points to be used, and only use those ones? And to doing this, we used an evolutionary algorithm. And again, we set up an empirical experiments with different models, different data sets to see if the algorithm really works. And this is a work which is currently under review from some time. So should nag the editor again. So, what we did is we proposed our solution, but which other solutions exist? And again, beautiful empirical research, we have a method for that, which is called systematic literature reviews. We all know this, so I can be quick about it. This is a study we did with colleagues from Delft, and I won't bother you with how systematic literature review works. I think most of us know it. Otherwise, there are many good references online. But basically, you set up a query with which you search the digital libraries or indexers. Here we had some replication going on, redundancy, in order to make sure everything was covered in the automated initial search. Then we set up some inclusion criteria. We conduct the snowballing. We have a data extraction framework, so a systematic way in which we say this is the data we want from each paper, and then we collect the results. For example, which data type is most used? We didn't know it before, but in Green AI, mostly images are used, followed by textual data, then numeric, video, and so on. And a lot of papers actually don't specify which data are used. It's kind of weird. Or again, which is the, and this was basically what you said before, is what we talked about a bit, is that a lot of papers, this was back in 2022, I think, or 23, I haven't a reference, focus on training for now. Consider both inference and training a bit less, and then even less on inference only, which is something I think we can improve because of what you said, Emilio. And going on, for example, the type of study which is presented in Green AI, we have actually a lot of solution, which is 51. Then we have some observational studies, so they just look at how much data it consumes, but they don't make any claim on how to the problem could be solved. And then some positions papers such as Green AI, we should do it, it consumes a lot, and so on. Which based on these results and how we started the talk, Logic Thread would say, wait a minute. So we said that many Green AI solutions exist. So this was one of the findings of the literature study. AI is consuming a lot. And the question is like, what is happening here? Empirical research. Can we use an empirical approach to answer that research question? And the answer is, yeah, of course. It's like, that's what we do. Galileo was throwing rocks from the leaning Pisa tower. Why can't we use an empirical approach to answer this question? So we set up an empirical experiment, right? Yes? No. So we could, maybe, but as Monty Python would say, now for something completely different, which is still empirical research, but it's not experimentation. Because, listen, qualitative empirical approaches. So, by analyzing software alone, I think we can never get the complete picture of software development, how it happens, the whole context, and so on. And to give you some examples of this, if we can only access software-centric artifacts such as source code, test suites, readmes, and so on, how can we retrieve the rationale of an architectural decision? I mean, you can think of some convoluted mining studies involving parsing Slack messages or mails to trying to trace back this, but it has a lot of then threats to internal and construct validity, I guess. Or, another question that is hard to be answered with an experiment or a mining study is how can we understand the motivation behind deprecating a software product? Maybe we can mine the user reviews and do some sentiment analysis on that. Or the question we want to answer, which is why Green AI solutions are not utilized today. Maybe we could set up an experiment or a mining study or whatnot, but I think there is a simpler way, which is we just ask directly the developer or whoever has a stake in the system. And I find quite intuitive. So each research question has its own research approach, which is best fitted. And this is where qualitative empirical approaches come into play. There are two books which are very good entry points for qualitative empirical research: the Qualitative Inquiry and Research Design. This is, I think, the third edition. There is a fourth which came out. And then a coding manual of some sorts. And this is then, in one way, let's say more how we collect the data and then how we analyze it, sort of. I think that they're quite complementary. I really thank Philip Kruchten for suggesting me this book. It's really amazing. Entry points, very high level, but very good references in there. What this book focuses on is focus groups. They're actually not in the book, but they're very used and very useful, I would say. Then they have grounded theory, which is something I used, ethnographic research, which actually some colleagues at my university, some researchers at my university are currently finishing on. So the ethnographic research is like you live in an environment for half a year, and try to understand what is going on there. Then more case studies is also something which is at the border between quantitative and qualitative research, and then the weird stuff like phenomenological research or narrative research, which I think it's extremely seldom used in software engineering, if not at all. I mean, a bit. And narrative research, I don't think I ever seen something like that. But going on, just to give you an example on how qualitative research works, this is something we did a couple of years back. Was founded by the Amsterdam Economic Board because they had problems with managing the energy availability they had in the Amsterdam region, because it's really small and a lot of people want to have their hyperscalers, which is not the best idea ever, maybe. But so how this worked, we had first of all a set of interviews that were just preliminary, exploratory, to have a bit of a sense of what was good to ask. Then focus groups following. So we sat down with multiple people and we said, look, this is what is happening. Basically, focus groups are really good, really nice, because you just have a topic, you let some experts sit down in a room, you throw a bowl, and then they discuss about the topic, and you just supervise the discussion, basically, and watch them play with the bowl. And what is and then the third phase, we had some working groups. There were a lot of people involved, I guess 30 in a single session of 1 hour. So usually want to keep this sort of things short, because after a bit people get tired, obviously. And here what is really important is, of course, in qualitative research, one of the key factors is you have to identify the right people. So if you have really smart and focused and expert people, the results will be much better than if you just randomly sample layman people on the street. And so, for example, here we had the luck to talk to a lot of very knowledgeable participants, most of which I can't name the companies they worked for, but for example, think of Red Hat was one of the software providers, VMware was one of the cloud providers, and other ones we can't name because of NDAs. But they were distributed in different ways throughout the phases. Because of the nature of the different qualitative research method we used. And we used something like, stickers, Miro boards, these sort of things are really helpful. This was still in COVID times. Imagining the havoc of having 30 people in a Zoom call working with Miro boards, but that worked. But usually stickers is something you want to use if you have a lot of people involved, so you can provide feedback, they think on their own, and then you discuss results together, opinions, and so on. And what we came to is sort of a landscape of solutions to improve the environmental sustainability of digital infrastructures, meaning both data center, hyperscalers, edge computing, and so on and so forth. Lots of things I won't go through, but maybe just one result I liked is this paradigm shifts, which will happen. So this is a temporal horizon, talk what is available today, what is happening, and that's like moving to the cloud. It's a way to optimize the sustainability of things. You just don't care. You pay someone to do it, and then cloud providers have their own problems of energy consumption, how much it costs. So they will do things like hardware, liquid submersion to improve the cooling, or have more efficient hardware and so on, cooled rooms. And this is, the current state is everybody's moving to the cloud. In a couple of years, we're talking 5 to 10 years, what will happen, we hope, is sort of flexible, distributed, and disaggregated data management, which means basically instead of having just these huge hyperscalers which consume a lot of centralized of energy in a centralized geographical area, think a block of a server house, which is what's currently happening. It will be more disaggregated throughout many places. And then in the last, more futuristic kind of timeline, which will be from 10 years and above, there will be hardware breakthroughs, such as, for example, non-von Neumann architectures, for example. Think of quantum computing, for example, which has a problem on its own, which is you have to keep it like at 0 Fahrenheit. So it's like, at absolute 0, which is kind of costly from an environmental point of view. But or neuromorphic computing, but people said, and it's not me that said, it's like also good thing is we had experts that back this up, is there will be this hardware breakthrough which improve the sustainability of data centers, basically. Of course, we had our little focus on AI-centric, cloud-centric, and software engineering-centric solutions, which we extrapolated from the interviews. And as one result I really liked, and I discuss a lot these days, is how the different scenarios of where computation will happen will be. And now what we have is huge hyperscalers. Hyperscalers is like server houses, right? So it's like you just have huge buildings with as many servers as you can get in there. But what will happen in the next phase is we will have a mix of remote clouds and micro clouds. And what will this will allow is to have prosumers. So instead of saying, we just have now all the servers and where the energy is consumed is in this area, we'll have also servers spread out in an area, and this will enable prosumers, which is basically you produce and consume energy locally. Solar panels, you have your solar panel and you produce it there and you consume it there. And then going forward with this, we'll have a seamless continuum of hardware resources which are shared. So I don't even care where something will be deployed from a hardware point of view. And in the end, what will happen is like following time, space, and energy. So maybe I want to train a huge machine translator somewhere. I just deploy, and then automatically through a smart grid, it will say, look, it's sunny in Spain today. We will train it there. Or nobody's using that server in Iceland. Do it there without carrying that much, and also based on the type of task, right? Is it the time sensitive? Is it not time sensitive? And so on and so forth. And the question then is like, okay, so we have all these solutions. Why are we not making AI greener yet? And this was also one of the results. And there are different type of challenges which we're currently facing. One is the lack of a leading champion. So this thing is not for free, right? So it's like, who's gonna take the risk and sort of the gamble to say, I want to improve my sustainability? Nobody does. So right now, they're trying to, but mostly it's what costs less and makes you show off better that you're sustainable and whatnot. You have all this zero pledges, which often you have to watch out a bit because they imply some sort of, for example, offsetting, which is not really what we want. So just throw money at the problem and say, you know what, we're consuming a lot, but at the same time we're planting trees in Australia, and it's not a point of, it's not how things work. So it's like there's not water scarcity, it's just a displacement of water around the planet. So you can't just say I consume here and I fix things in another region. Unfortunately, not how it works. There's also a scattered landscapes. You have a lot of different technological frameworks, let's call them. So it's really hard to have solutions which work in general. There is, of course, a resilience to change. Things work the old way. Why should it change now? Which then leads to what will happen if I apply a certain solution? What are we losing? What are we gaining? And so on. There is for sure a lack of missing off-the-shelf solutions, also because there is this sort of resilience to change, which then leads companies to not apply what we as researchers can only implement till technological readiness level like 2 or 3 maximum. So there's for sure you can't go to a software marketplace and say I want something to improve my energy efficiency. I don't think that's available. There are some endeavors that try to do this, but nothing really ready yet, I think. And of course, there is a lack of knowledge and awareness on all of this. It's like, that's usually how I start my talk, is like, how much it is consumed, because it's not something that we think of. It's like, I'm just using my phone, I'm using WhatsApp. I consume just my energy of battery. It's not, but that's not exactly how it works, right? So how can we make green software first? Class requirement, and here again this is something that we're like sort of the final results, and something which came through to some elaborations. First, you need clear-cut standards and metrics. So usually, and I use it to, CO2 is really nice to say it consumes this much CO2, but usually it's a very fiddly metrics, because it depends on where the energy is produced. So it's really hard to basically compare CO2 results, because maybe, again, it was a sunny day in Spain, so you trained your model there, but it's like, how much energy does it consume? So in the raw metric, you can't really say. And it's really hard then to compare. It's like, yeah, it was like a rainy day in Pernambuco, and I trained my model, and it's this much CO2. Really hard to compare results in CO2. Energy is much better, at least from a research point of view. Then we need, of course, share responsibility across the whole supply chain, and this implies also us, both as researchers, but also as final users, to demand at least clarity in terms of the energy consumed by the services we're using. Maybe activating taxation strategy. Money is something that usually people understand quite well. You can just say, you consume this much energy or CO2, well, then we will tax you this much. And that will for sure sensibilize companies in being more sustainable. Maybe hard to bring it to the regulators, but who knows? And then awareness creation and sustainability skill training, talks like this, courses at universities, specialized courses, and so on. Maybe as a final thought on empirical engineering and green software, and this then closes my talk. There's something I feel it's still kind of hard to get into, is that a lot, and again, it's like software engineering, mostly qualitative stuff, but I think we can't really hide that qualitative has its own advantages, and they should be complementary, right? So it's like, you can't just say, it's like we are quantitative and that's exactly what we have, and so like let's discard off the quality stuff. And this is a lot of, if you went to a ISTI or whatnot, it's like 90% quantitative, and the 10% that remains is qualitative, and they tried their fourth resubmission to get that paper in, because you have things like, oh, it's subjective, you're not complete, it's biased, and so on and so forth. So I think that, as a research community, we have to better accept that both quantitative and qualitative approaches have their own potential. And at the end of the day, both are tools, and I guess for fixing software quality, so fixing green software, you need a bit of the mix of the two. This ends my talk, and if you have any questions, more than happy to answer.
Thank you, Roberto, for the very insightful presentation. So,
sure.
Questions from the audience? So that you are thinking, it's more like a curiosity, because in the examples you showed, like software consumption, like in general, I think the case was grep, and then for training models, and I can think about many contexts in which you could apply something similar for software testing, like generation, amplification, and combined with the tools, all these sort of things. So I'm just curious to ask you, what are the things that that have already been done in this software field? In the software testing context, like for consumption?
Extremely little. So I know there was
good news, actually.
Huh?
So that's good news, actually.
Yeah. I guess there was one paper which I think was at ISTI this year, which is from Andy Zeidman, which goes something on the line of the hidden cost of software testing, something like that. And they looked at how much a test suite consumes. I guess he did also something regarding continuous integration, what a really top-notch study, different hardware setting, etc. But that I'm aware of, it's like that. This another study with a similar approach by the I think it's called Green Lab Group in Portugal. And that's it. Then I mean, there will be something else out, but not that much, because the paper from Anni Seidman was really high level, and I guess reviewers were really thorough in their analysis. And that's like the state of the art. It's like still not presented, or was presented. I don't know if it was ICSI or EST.
EST, yes.
EST,
He presented
yeah, damn it.
a couple of papers in about
But it
this.
was like this year or something, right?
This year,
Yeah.
in Lisbon, yeah. Okay, thank you, Roberto.
Sure.
But I have two questions. They are both provoking. Okay,
Beautiful.
one of the things that you measured is what is the energy consumed for online meeting.
Yeah.
But the alternative is to take the airplane and go there. So
No.
okay, there is a bigger picture that is not only about software. I think that if we look to consumption and the green and the planet only from one corner, we are not going to win. I need, we think, some holistic view.
No, sure. So there are studies on the costs of the environmental cost
Because
of going to conferences, for
online
example.
meeting is the holy grain, actually, because they allow to save a lot of money, right?
Yeah, but then maybe I would suggest use Zoom, for example. In this case, I think one of the findings was among the two, better to use Zoom. Then, of course, in this case, this was really focused on, I have my phone, maybe I have low battery, I have to improve. So it's like not that this like dramatically changes the world, but it's just an example on how you can see the energy consumption of applications. I'm not saying like fly there, but just say, maybe if do we really need the camera? Maybe, because there is also a social cost to it, right? So it's like, maybe you're sleeping and I'm talking to someone who's sleeping, and if I see that the webcam is on, someone dozing, and say, hey, are you not following? While if I have the camera off, so it's like a lot of implications. But for example, do we really need cameras all the time? Or if you don't move or you're not there, just make it automatic to switch it off. So
that was one question comment. The second one is, you started with the example of GPT and so on. Yeah. So, but now all the study that you brought are about software, but a big cost is data, right? Because today we are overwhelmed by data. Data is everywhere, is in the phone. In my phone, I don't know how many thousand pictures I have, and those take space, consume battery. So, and if you multiply these for all the world people, and so is there also some ongoing research about green data engineering or something? Because I think that the real cost today maybe is not the software but the data.
Do you want to work on it? I think not, honestly. Yeah, back in the day, we wanted to do something on that. We didn't. And now it came back to me like after years. I haven't looked into it again, but at the time it was like nothing. I mean, there are ways to like cold storage and whatnot. So it's like ways to really make energy storage efficient. But like, what's the impact of storing one photo against 10,000 or 1 million?
No,
this is not something that I'm aware people did yet, because we're going to do it.
Okay.
Thanks for the note. I noted it down. I really forgot.
Okay, so let us thank our speaker again.
Thank you.
Thank you, Roberto, for the great talk.
Yeah, thanks for the invite.